I'd like to show you a couple of examples of using uh, regression analysis to predict, in this case, future sales. First, we'll talk about a simple linear regression. In this case, we have a construction company, and it's trying to determine if there's a correlation or some kind of a mathematical relationship between its sales, which you see in the left-hand column in hundreds of thousands, like $600,000, and payroll, local payroll, which is in $100 million, 300 million, the first case. And so, what we would like to know is there a relationship between the two? And they gave us looks like 6 years worth of data here. And so the first thing we would do, these are ordered pairs, $600,000 right here goes with this $300 million payroll, and $800,000 in sales goes with $400 million payroll, and so forth. So when we have these ordered pairs and we want to determine if a correlation exists, first thing we would do is as we have right here, is we would see if there is a relationship, a graphical relationship. And you do that by going to Excel and scatter diagram. The X variable is really the independent variable. We can't control that. So in that case, it's payroll. And the Y is sales. That's the thing we're trying to learn something about or predict. And so if you do the scatter plot, you notice that the blue dots, that's what we're interested in now, the blue dots, they're kind of close together. There's a little problem right in here someplace, but they're generally close together. You notice it's a positive relationship. It goes to lower left to upper right. And they didn't do it here, but what I can do is, and you can do this on any scatter diagram, take any dot, right click it, and click on Add Trend Line. It'll give you this menu on the right here. Go all the way down. They already have the trend line in, by the way. That's the blue line. But what I want to show you is this. Click on Display Equation on Chart and click on Display R squared value on chart. And it does just that. We'll move them over here so you can see them. It gives you the equation, the regression equation, the predicted equation. What it says is y equals 1.25x plus 2. 1.25x plus 2. Well, in our case, the y is sales. So what it'll say is sales, the amount of sales, is going to be equal to 1.25x. In our case, x was payroll, times payroll, plus the constant 2. So it gives it to you right here. Now, if it doesn't give it to you, the resulting Excel output is right here. It gives you the coefficient, which is 2. That's the constant. And then it gives you the x variable coefficient. This is really the slope of the line. You remember y equals mx plus b? Well, m is the slope of the line. That's 1.25 in our case. And so all we have to do is put in a value for payroll, any payroll, and it'll come up with a predicted sales. Now, I also want to point out that it gives you a value of r squared here. Well, if you take the square root of r squared, you're going to get r, which is the regression coefficient. Remember r, we talked about this. It's either goes from -1 to +1. The closer to +1, the better the positive relationship. Well, this one is 0.833. If you take the square root of 0.694, you're going to get 0.833. And so 0.833 is out in here someplace, which means it's a good positive relationship between these two variables. In other words, the payroll is a good indicator of what future sales might be. Now, r squared is called the coefficient of determination. I think I saw this in a quiz or something that you're going to do. Coefficient of determination, that's R squared. In this case, it's 0.69, so we'll say 69.4 in percent. It's always in percent. What it means is it tells you how much the X variable, in this case payroll, impacts the Y variable, which is sales. And so we can account for about 69% of sales due to payroll alone. The other 31% of sales, you've got to make 100%. The other 31% of sales are due to other factors that impact construction. Maybe weather, for example, availability of supplies, so on and so forth. They account for the other 31%. So remember coefficient of determination. What it is, it's given to you both on the chart here, if you click, like I said, right click on any dot, or it's given to you right here. This ANOVA stuff for this class, you can kind of forget about it. We don't get involved in that in this class. Now here is the same problem. Now you notice that remember our formula was sales equals 1.25 times payroll plus the constant 2. There they are once again. So if the local payroll is $700 million, what we could do is put that in here plus 2. And if you do the math, you'll find, 1.25 times 7 equals 8.75. 8.75 plus 2 equals 10.75. So that's how they got the forecast for $700 million in payroll. Now, one other thing. Over here, it talks about errors. And so, in the case with $300 million in payroll, if you put 3 in, 1.25 times 300 million plus 2, you're going to get this forecast, 5.75. Well, in actuality, they had $600,000 in sales. That's a real number. The predicted equation said 5.75 you should get. So you see the error is 0.25. And these are error terms, which we're going to learn about here in Unit 6. Absolute just means forget about plus and minuses. They're all plus. You square it and you get the absolute percent error. So the common error terms are the mean absolute deviation. You take the average of those, you get about 0.83. And the one that most people use is the mean absolute percent error, which is 12.56%. So you're talking about a 13%, approximately 13% error using this regression equation. Again, there's the correlation we talked about earlier and the coefficient of determination that we also talked about earlier. So this isn't difficult. Use Excel and you should be in pretty good shape. This is linear because there's only one variable. Now, let's talk about multiple regression. In this case, this realty company has data on the selling price of houses versus their square footage and age of house. You notice we have two variables here, X1 and X2. Previously, we just had one, which was payroll. Now we have two. So what we want to know is there a relationship between square footage, the age of the house, and the selling price? The selling price is the thing we want to predict based on these two variables. And so what we're going to do is we're going to, instead of having y equals mx plus b, the way we did before, we're going to have y equals the constant, I'll just call it c, plus x1 times its square footage plus x2 times the age of the house. So you see, we have two variables here. Well, we can find that equation using Excel. And let me do this. Let me stop inking here. Let me go into Excel. New one. Okay. Okay, what I'm going to do is I am going to go into, oh, I can do it right here, I think. I don't need another one. I think I could do it right here. Yeah, let me do it right here. Okay. What I can do is I can go into data analysis, and go into regression, where here it is right here, regression. Okay. Now it wants to know what is the Y range. Well, again, what we want to know is the selling price. So we're going to do this. And then it wants the X range. Well, now we have two X's. So what we do in this case is we left click and hold all of them. You know, so I did all of them. Oh, wait a minute. Let me cancel that. Let's start again. I may have done something wrong. Let's do the Y's again. Okay, now let's click on that, and let's do both of them. Okay, now we're all set. So what we want to do is to say, okay, and we're going to come up with an output, Excel output. And see, this is what on your projects that you hand in, this is what I want to see. I don't want to see the input, I want to see the output. Okay? But anyway, what this says is, right down here, it says that we have an intercept right here. We have an X variable and a Y variable. So what we're going to have is we're going to have Y equals the intercept, the constant, which is 14,630, it looks like, plus 43.82, I'll call it. That's the X variable, times square footage. That was our X1 term, if you recall. Then we have minus 2898.7 times the other variable, which was age of the house. Okay, so the selling price, instead of Y, we could have said selling price, is equal to 14,630 plus 4382 times the square foot minus 28,980.7 times the age. And so if we go back here to Jenny Wilson, marketing, you notice that right here, what is the forecasted selling price for a 2,500 square foot house that is 10 years old? 2,500, 10 years old. So what we're going to do is we're going to go back in here and we're going to say, okay, we have 2,500 square feet and our age is 10, okay? And so we're going to do the math. It's 0.7, and we got 43.82 plus 14,630. So if we, let me get my calculator out, if we have 43.82, and I rounded so it might not be exact, times 2,500, that's 109,550, minus 28987, we just multiply them by 10, 146,630. So if you do that, 146,630 plus 109,550 minus 28,987, we get 227,193. 227,193. That should be the predicted selling price for a house that has 2,500 square feet and is 10 years old. 227,193. So if we go back to the original, yeah, that's what they have right here. You notice 227,192.44, pretty close. So that is how you use multiple regression and Excel. Now you notice also here that they have error analysis. We have the forecast for a $95,000 house, which sold with 1,926 square feet and 30 years of age. Well, our equation said that should be 144,066. So you notice there's quite an error there. There's 49,066. That's a big error. And again, what I suggest you do is look at the mean absolute percent error, the average right here, which is about 12%. That's a good error to use, I think. And you'll notice correlation here again of those two variables with selling prices. Pretty good, about 82%. So these are two examples of linear regression and multiple regression for you to use here in Unit 6. If you have any questions, please email me, afiducia@kaplan.edu.